where essentially it spins in a circle and it's a cylinder, and then once it reaches a certain speed, the floor drops out, and then you're still against the wall spinning, and in theory, you don't fall down. And that's due to the coefficient of friction. In this case, it's static friction because you're not moving up and down the wall. You're still stuck in that one place.
Okay, so first we have to go through the protocol. Step 0, is this a dynamics problem? Yes, it is, because we're solving for the coefficient of static friction, and friction is a force. Step 1, we say, oh shit. Step 2, the sum of the forces is equal to mass times acceleration. Step 3 is our free body diagram. So you have your normal force acting in this direction because he is up against the rotor ride, and so it's pushing on him. And then we have the force of gravity acting downwards. And we have the force of friction, static friction, acting up because he's not on the bottom of the rotor ride, so there has to be some force acting up, pushing him up. Step 4, is it in equilibrium? No. So we can say that the forces is equal to mass times acceleration again. And step 5, we solve.
We're going to convert our 15 revolutions per minute to radians per second, so we yield angular velocity. So we cross out our minutes and we get seconds, and then our revolutions cancel, and you multiply by 2 pi, and it yields 1.57 radians per second.
So first we're going to sum our forces in the y direction, and it's going to be force of friction minus force of gravity because the two forces are going in opposite directions. And the person is not moving, so the sum of forces in the y direction is equal to 0. So force of friction equals force of gravity. Force of friction equals mu times normal force, which equals mass times gravity. So we're going to solve for mu. So this is the equation. Next, we're going to sum our forces in the x direction, and the only force acting is the normal force. And then it's going to be mass times centripetal acceleration because it's moving in a circle, which equals normal. And then that's the equation to find the normal, which we need to solve for mu. We're going to solve for mu, and we didn't know the normal force, but we just found it now, so we substituted in there to get this equation. Now the masses cancel out. So we plug in gravity, our omega, and our radius, and the meters cross out, the seconds squared cross out, and we get approximately 2.
The minimum coefficient of friction of the material on the wall needs to be at least 2 to ensure that the person doesn't fall down when the floor drops out. And this is necessary because you can't control what type of clothing the riders wear. To see how a rotor ride works in action, we headed over to the Cal Poly Rec Center. We recruited some eager volunteers and placed them inside a swimsuit dryer. Then, after spinning our volunteers in the rotor ride for a few seconds, we lifted the top to see what was happening inside. A common misconception is that when you are riding a rotor ride, you think that there's a force pushing you against the wall. This is false. There is no such thing as a centripetal force. As we showed in the free body diagram, there is only the normal force of the wall, force of gravity, and force of friction in the y direction. The reason why you feel like you are being pushed back is that your body wants to continue in a line tangent to the curve, yet the walls of the rotor ride keep you going in a circular motion.